we're asked to solve for all the reactionary forces on the supporting bridge. Let's go ahead and label our reactionary forces first. We know a roller has one reactionary force in the perpendicular direction. We'll call it RCY, or reactionary force at joint C in the Y direction, or we can call it Ricky for short. And then we've got one that's perpendicular at joint A as well, reactionary force at joint A in the Y direction, or good old Ray. And as we know, pins have two reactionary forces, one perpendicular and one parallel to keep it from moving sideways. And we'll call this reactionary force A in the X direction, or good old Rax. And the question is, what does Rax equal? What does Ray equal? And what is good old Ricky? And so to solve for this, we're going to use the sum of all forces. And let's start with the sum of all forces in the X direction. Well, we know they have to equal 0, so the bridge isn't sliding left or right. And what are my forces in the X direction? Well, if we look, there's only 4 forces in the system, and only one of them is going the X direction, and that's good old Rax. Well, if all of my forces in the X direction have to add up to 0, and there's only one, then that number has to be 0. So we're done with our forces in the X direction. Rax has to equal 0. From here, we can use our other forces, use the sum of all forces in the Y direction equals 0. And in this, we have a couple more examples, or a couple of more forces. So we got Ray going upwards, that's in the Y direction. We've also got Ricky going in the Y direction. And of course, we've got our force of gravity at B, which is just 500 pounds. And so in order for this statement to be true, for all 3 of my Y forces to equal 0, what we have to say is our upward forces have to equal our downward forces. And we look, Ray and Ricky are going up. And so I can say Ray plus Ricky equals 500 pounds. And we know these have to add up to 500 because they have to cancel it out. If they don't cancel it out, then the bridge is collapsing and everybody's dying. Ah, the humanity! But the problem is there's too many variables in this equation to solve for Ray or Ricky, so we have to go about it another way. And that's where moments come in. That's where we say the sum of all moments equals 0. Well, there are 2 moments. There's a moment at point B and there's a moment at point C, because what does it need? It needs a force and a distance. Well, C has a force. It's going up, and then it's got to go towards the pin. So it's going up and to the left, which makes it counterclockwise. And then we have another force with another distance from our pin that's going down, so we'll make our moment continue to go down, and then it will bring it towards our pin. And this one's going clockwise, and we'll call this one moment B. And we'll call this moment at point C, moment C, because that makes sense. And then we can say, well, these equal 0. The sum of all moments equals 0. We got 2. It's moment C plus moment B. And you might say, well, what about the moment at moment A? Or what about the moment at point A? I'm sorry. And I meant to write moment B there. I don't know why I wrote moment A. I guess I was saying it. But what about the moment at moment A, or the point A? Well, there is no moment at point A. Because remember, there is no moment at the pin. Because a moment requires a force and a distance. And while moment A, point A has a force, it has no distance from the pin. So there is no moment at joint A. But we do have a clockwise moment, as we said a second ago, at moment B, and a counterclockwise moment at moment C. And in order for these 2 moments to add up to 0, they have to cancel out. So in other words, moment C has to equal moment B, because all of my clockwise moments have to cancel out all of my counterclockwise moments to add up to 0. And I only have one of each in this case. Well, a moment is just force times distance. Well, what's the force at point C? We don't know. That's the whole point of this. So we know it's Ricky. It's some number multiplied by the distance, which we do know is 100 feet. And we can set that equal to moment B, which is also a force times distance. Well, the force at moment B is 500 pounds. And the distance at moment B is 55 feet from the pin. So now we can just solve for Ricky. Well, first we need to simplify. We say 500 times 55. And so we get moment B is 27,500, and we can just bring down the equation from here. And it's 27,500 foot-pounds, because it's a moment, or work. And then to solve for Ricky, we'll just divide by 100 on both sides. We get 100 feet cancels out on the left, and feet cancel out on the right, and we get, well, whatever 27,500 divided by 100 is, which is Ricky equals 275. And so we can fill that in over here. Ricky equals 275. And the only thing left is to solve for Ray. Well, we have everything we need. We can rewrite this equation where we plug in Ricky of 275 equals 500. And then we simply subtract 275 on both sides. And it cancels out on the left, 275 pounds minus 275, and we get 500 minus 275 pounds. So 500 minus, times, minus 275. And we get 225, so we get Ray equals 225 pounds. And so what does this mean? Well, this makes way too much sense. There should be a little bit more at Ricky, since the force of gravity is a little bit more towards Ricky. It's 55 feet away from the pin, which means it's 45 feet away from the roller. So it should be a little bit bigger. So this answer